Welcome to this explainer. Have you ever actually stopped to wonder what exactly powers the complex calculations behind, well, everything? Your savings account, national demographic shifts, or even the digital algorithms curating your feed right now. Spoiler alert, it isn't magic, it's math. Today, we're popping the hood to look at the engine of reality itself. We're going to unpack integral, radical, and rational exponents, and I'll show you exactly why they are absolutely essential for making sense of the business and social world around us.
Okay, here's our roadmap for today. First, we'll hit real-world growth mechanics, then integral and rational exponents, followed by radicals and their roots. After that, we've got the power of a power, rationalizing the denominator, and we'll wrap it all up with their exponential impact on society. Let's get to it.
Section 1. Real-world growth mechanics.
So, we see equations like this literally all the time in finance. They're present value calculations, and they run entirely on negative exponents. Let's say you know your money can be invested at a 9% annual compound rate, and you want to hit 10 grand in exactly 7 years. Well, how much do you need to invest right this second? To find out, you calculate 10,000 times 1.09, but raised to the negative 7th power. And that negative exponent right there? That's the secret sauce. It's what allows modern banking to essentially reverse engineer time and money.
But it's not just banking. Mathematical structures directly dictate our society through things like tax brackets. Think about the 2007 IRS tax code for a single person. The tax due isn't just a flat rate, it's broken into these strict algebraic intervals. If your income falls between, say, $31,851 and $77,100, your base tax is a flat $4,386.25, plus an additional 25% over that specific threshold. Grasping how these structured mathematical intervals actually dictate our economy? Well, that's step one in seeing why the underlying algebra matters so incredibly much.
Section 2. Integral and rational exponents.
So, what actually is a rational exponent? The crucial point to remember here is that a rational exponent, which is just an exponent written as a fraction, like 1 over n, is really just asking a question. It's asking, what number, multiplied by itself n times, gets you the base? Whenever you see a base number raised to a fraction, it is perfectly 100% equivalent to taking the nth root of that base. Once you realize it's just a root in disguise, working with these expressions suddenly becomes incredibly intuitive.
Let's put that into practice. Whether you write 8 raised to the 2/3 power or the cube root of 8 squared, the value is exactly 4. Let's break that down. It's actually pretty cool. You can rewrite the cube root of 8 as 8 to the 1/3 power. Now the cube root of 8 is simply 2, right? Because 2 times 2 times 2 is 8. Then you just take that 2, raise it to the 2nd power, and boom, you get 4. This kind of interchangeability, it's an absolute game changer for simplifying complex financial and demographic models without losing a shred of accuracy.
Now think of this next part as our foundational toolbox. It maps out exactly how positive real numbers interact with both integer and rational exponents. We've got everything from the product of powers, where you just add exponents when multiplying the same base, all the way to the power of a quotient. Every single rule here is designed to give you a clear roadmap for simplifying really messy variables. And the best part? All the rules that work for your standard integer exponents work absolutely flawlessly with rational exponents too.
Section 3. Radicals and their roots.
There's a famous saying in math that goes, every compound growth formula is the power rule in disguise. It perfectly bridges the gap between abstract math and the cutthroat business world. The power rule is basically your gateway to solving complex growth models. You're going to see it pop up wherever a quantity grows exponentially with a compound exponent. Honestly, whether you're looking at a macroeconomic growth model or a physics decay equation, spotting the power rule hiding inside the formula is the key to unlocking the whole thing. Let's get some basic vocabulary out of the way. For example, if we're looking at the 8th root of 144, that 8, that's the index. It sits right above the radical sign on the left and tells you exactly what degree of root you're dealing with. And the 144? That's the radicand, just a fancy word for the number sitting safely inside the root symbol. Getting comfortable with these terms is crucial. It's like learning the local language before you try to navigate advanced modeling. Now, the logic flow here is super simple to remember. Root first, then power. This lets you safely move the power to the inside of the root. Here's the trick though. If the index is odd, go for it. You can seamlessly pull that power inside. But if the index is even, you gotta be careful. Even roots of negative numbers completely break the rules of basic algebra.
So, as long as you know your variables are strictly non-negative, you are totally clear to simplify by bringing that power inside.
Section 4. The power of a power.
Okay, getting this next rule right is quite literally the difference between calculating a 30-year mortgage perfectly or completely crashing a multi-million-dollar financial simulation. When you're dealing with a power of a power, you must multiply the exponents. You never, ever just add them. This is where people constantly trip up. They confuse multiplying two separate bases, which is when you do add the exponents, with a base raised to a power that's then raised to another power. Think about x cubed all raised to the fourth power. That becomes x to the 12th. If you just add 3 and 4 to get 7, your entire calculation is garbage. Scratch that. It's not just garbage, it's completely mathematically broken.
So, when you're tackling complex, real-world variables, you always want to pick the rule that matches the outermost structure first and then work your way inward. It's like a puzzle. Most real-world exponent problems are going to require using 2, sometimes 3 rules at once. If you've got a coefficient inside parentheses, say 2x cubed, all raised to the 4th power, that outer exponent applies to every single factor inside. You have to distribute it to the 2 and to the x cubed, multiplying your exponents as you go.
Section 5. Rationalizing the denominator. Sometimes our math engine gets a little messy, so we need a way to clean up radical denominators to make our equations actually usable. Enter this brilliant 3-step process. This is how mathematicians hack their way to clean denominators, and it relies heavily on the difference of two squares when using conjugates. Basically, if your denominator is a binomial with a square root, like a plus b, its conjugate is a minus b. Multiplying them together is like magic. It entirely strips away the outer and inner product terms, leaving you with just the squares of the first and last terms. In one move, it totally destroys the radical on the bottom.
Let's see that in action. Take 6 divided by the square root of 5. By multiplying both the top and the bottom by the square root of 5, the bottom just becomes the square root of 25, which evaluates perfectly to 5. And notice the result. 6 times root 5 all over 5. Boom. The simplified expression has absolutely 0 radicals on the bottom. That is the ultimate goal here. Leaving an expression without a radical in the denominator isn't just neatness, it's standard practice, and it makes further calculations in fields like calculus and engineering 1,000,000 times more manageable.
Section 6. Exponential impact on society.
Let's zoom out a bit. Every single one of these fields relies entirely on the power rules we just explored. Seriously, annual financial compounding turns into monthly and then daily compounding, all by leveraging the power rule. A population doubling every generation? That relies on nested exponents to forecast centuries of growth. Even astronomers at NASA use Kepler's third law, which runs on fractional exponents, to figure out planetary orbital periods. It's literally everywhere.
Whether we're analyzing healthcare costs or predicting global populations decades into the future, decimals and fractions act as the exponential engines driving the data. For instance, models predicting India's population growth use formulas where time is raised to a rational decimal exponent, 0.13 to be exact. Over in the US, healthcare expenditures follow a massive exponential growth curve based on time. It is truly mind-blowing when you realize that without a firm grasp of radicals and exponents, we literally wouldn't be able to read the data that is shaping our entire future.
So I want you to think about something as you leave this explainer today. Whether it's the interest silently compounding in your savings account, the shifting population of your city, or the complex algorithms curating the media you consume, what exponential curve are you on? Because make no mistake, the math of exponents is already shaping your future. Understanding these rules, it isn't just about passing a college algebra test. It is about seeing the fundamental code that dictates reality. Keep learning, keep questioning, and I'll see you in the next one.